Hello and welcome to the last lesson of this semester. At the beginning of the semester, we introduced this question that was supposed to be kind of the guide to our entire semester, which is answering the question of what is light. So we looked at waves in general, right, where we know that light is an electromagnetic wave, even if we don't really know what that is. We looked at the mechanics of waves, right, what they do, things like reflection and refraction, total internal reflection, and the like. And that's explaining what light does, but it's not explaining what it is. And then we started diving into electrostatics, and we introduced this very important concept of the electric field. But looking at that subject, we wouldn't necessarily expect that it would have anything to do with light. So we're going to round out the semester, but to do that, we've got to introduce a couple of concepts that we didn't have time to get to. So we're going to introduce a couple concepts really briefly, and those two concepts are going to be magnetism and Faraday's law. And with these two general principles underneath our belt, we're going to try and answer this question of what light is, what's an electromagnetic wave, and maybe the most important question, how is light capable of traveling through a vacuum, right, without a medium? All right, so magnetism, I would say, is the study of the magnetic field. All right, so just like an electric field is being created by stationary charges, or a collection of charges, net charges, we can also have a magnetic field that's being created. And when I'm looking at magnetism is going to talk about all the different ways that it can create magnetic fields and all the different effects that magnetic fields can have on moving charges. So really one of the main things that we want to be introducing in this video is this idea that there is a thing that's called a magnetic field. Right now, one of the ways that I can create a magnetic field is through what's called a permanent magnet. Now, a permanent magnet would be like the sort of magnet that you would find on your kitchen fridge, right? Or maybe you've seen the sort of characteristic horseshoe shape for a magnet where I've got a north and a south pole that it's written on there. And what this permanent magnet is doing, right, it's made of a particular kind of material and it's creating a magnetic field. Right? So, for example, a magnetic field that's going from the south pole to the north pole, looping around and through my magnet. And I can represent the magnetic field with this letter B. Right, so one way is that if we have certain materials like iron, which have this property of being magnetic, and they're capable of creating a magnetic field. Another way that we can create a magnetic field is through moving charges. So we had just started to dip our toes into moving charges when we started looking at current. So for example, if I have a wire that's a current carrying wire, right? I've got a current that's moving through it, a bunch of charges that are moving through this wire. I'm going to be creating a magnetic field in the vicinity of this wire that's going to be forming these little loops around my current carrying wire. So another way is that moving charges are going to create this magnetic field. And the last way, and perhaps the most sophisticated of the three, is that a time-varying electric field is able to create a magnetic field. All right, so I have an electric field that can be getting stronger or getting weaker at a particular point in space over a period of time, right? That the electric field is changing in time at a particular point in space, and that's going to be able to create a magnetic field as well. Now, it's this last way of creating a magnetic field that we're really interested in today with answering this question of what is light. So to represent, or the law that's going to represent this time-varying electric field is called Ampere's law. It's one of Maxwell's 4 equations, which he got to put his name on because he kind of synthesized them mathematically, even though all of the equations were created by other people. And there are a lot of different ways that you can write down Ampere's law, but what I'm going to do is I'm going to write down the truest one, I guess would be a way to say it. This is the equation that I really started to look at when I was in my own junior level physics class in college. So I'm going to write this down. Don't freak out. All right, so there's a lot in this equation that we don't know, and there's some that we do, about 50-50, okay? So, first of all, this whole part of the equation, probably don't know what this is. Not even really going to explain it. But what we do know now is this variable B. This is my magnetic field. We're familiar with our constant of epsilon naught. Mu naught is another constant, 4 pi times 10 to the minus 7. It's something that comes up when we're talking about magnetism, so we didn't quite get far enough to see that constant, but it is just a constant. It's on your equation sheet. And then we know that this is the electric field. And this is time. All right, and these small lowercase d's or deltas, this is a derivative. Now, a derivative is going to tell you that the rate at which something is changing. So this whole final term here, this dE over dt, this is saying that we're looking at an electric field and how that electric field is varying in time. All right, so this entire last term here is my time varying electric field. And my time varying electric field is going to create a magnetic field. All right, so this is the law that's telling us about the relationship between the electric field and the magnetic field. Okay, now moving on, we're going to look at Faraday's law, the objective best law in physics. And Faraday's law is going to look very similar. We're just going to be taking this relationship and we're switching it. All right, so if the Ampere's law is saying a time-varying electric field is going to create a magnetic field, then Faraday's law is saying that a time-varying magnetic field is going to create an electric field. So again, this term on the right-hand side, this is my time-varying magnetic field. And this is going to create an electric field. All right, so this is the sort of thing that's responsible for example, generators. All right, if we're generating electricity at like a power plant, one of the ways I can do this is I can create a time-varying magnetic field. Simple way to do that is take like a permanent magnet and just wiggle it around, right? And that's going to create a varying magnetic field. And then I can create an electric field which can drive current through a wire. All right, so we can generate electricity this way. We can do other things as well. Like, for example, any sort of metal detector is probably at some level using Faraday's law. As a metal object moves, right, generating a current that's able to be detected by your metal detector. All right, so tons of applications of Faraday's law, the link between electricity and magnetism. Now, if I put these two things together, what I'm saying is that if I have a time-varying electric field, so I'm just going to represent this by saying my electric field is a function of time. If I have a time-varying electric field, that is going to create a time-varying magnetic field. And if I have a time-varying magnetic field, I'm going to create a time-varying electric field, and so on and so forth, right? It's continuously generating an electric, then magnetic, then electric, then magnetic field. Now, part of what has to be true is that the electric and magnetic field have to be a particular kind of time varying. And a really good way to do this, or a really simple way to do this, is if my electric field is sinusoidal. So if I have my electric field that's being represented by a sine function, where sine on a graph is going to look like a wave. Right, it's going to go up and down, then up and down. Where this omega here is related to the frequency of that wave, right, and this is my amplitude. So if I have an electric field that's varying sinusoidally, it's going to create a magnetic field that's varying sinusoidally, which is going to create an electric field that's varying sinusoidally, and so on and so forth, and this cycle is going to just continuously be repeating. And so the result of this cycle is an electromagnetic wave. Right, where my electric field is in this diagram here, constantly pointing up and down. Right, so each of these lines is talking about the direction that my electric field is pointing, right? Slowly increasing and decreasing as we work our way through space. And then perpendicular to that, I've got this magnetic field that's being generated, which again, the direction is represented by these small lines, and it's slowly increasing and decreasing relative to space, creating this wave that's capable of propagating perpendicular to both the electric field and the magnetic field. Right, and this is an electromagnetic wave. So unlike a lot of the mechanical waves, the waves that required a medium, right, some sort of force and the constant interaction between molecules in the medium, right, with an electromagnetic wave, the electric field is creating a magnetic field is creating an electric field, and it forms a self-propagating wave. And so this is also going to explain how it's possible for an electromagnetic wave to travel through the vacuum of space, right? It is its own source of energy, and so it's able to continuously propagate over millions upon billions of miles of space without being altered at all. All right, and so that's it. All right, this is kind of the somewhat cursory, somewhat detailed explanation of what light and an electromagnetic wave is, building on some principles that we didn't quite get to, but I wanted to see what would happen if I got to the end of the course. All right, so that's it.